Analysis of variance involved examining the relationship between a categorical explanatory variable and a quantitative response variable. Next, we're going to consider inferences about the relationships between two categorical variables. The statistical test that will answer this question is called the chi-square test of independence. Chi is a Greek letter that looks like a large X, so sometimes you'll see this test denoted with an X squared. For this statistical tool, let's start with a new example. In the early 1970s, a young man challenged an Oklahoma state law that prohibited the sale of 3.2 beer to males under the age of 21, but allowed its sale to females in the same age group. The case was ultimately heard by the U.S. Supreme Court. The main justification provided by Oklahoma for the law was traffic safety. One of the three main pieces of data presented to the court was the result of a random roadside survey that recorded information on gender and whether or not the driver had been drinking alcohol in the previous 2 hours. There were a total of 619 drivers under 20 years of age included in the survey. On the left, you can see what the collected data look like, and on the right is a two-way table summarizing the observed counts in the roadside survey. Our task is to address whether these results provide evidence of a significant or statistically meaningful relationship between gender and drunk driving. Both variables are two-valued categorical variables, and therefore our two-way table of observed counts is a 2x2. The chi-square procedure is not limited to 2x2 situations. It can also be used for a larger number of explanatory categories. The key to reporting appropriate summaries for a two-way table is deciding which of the two categorical variables plays the role of the explanatory variable and then calculating the conditional percentages separately. That is, the percentages of the response variable for each value of the explanatory variable. In this case, since the explanatory variable is gender, we would calculate the percentage of drivers who did and did not drink alcohol for males and for females separately. Here's the table of the conditional percentages.
For the 619 sample drivers, a larger percentage of males were found to be drunk than females, 16% versus 11.6%. Our data, in other words, provides some evidence that drunk driving is related to gender. However, this in itself is not enough to conclude that such a relationship exists in a larger population of drivers under 20.
We need to further investigate the data and decide between the following 2 points of view: that there is no difference in the drunk driving rate between males and females under 20, our null hypothesis, or that there is a difference in the drunk driving rate between males and females under 20, our alternate hypothesis. In other words, is the evidence provided by the roadside survey, 16% versus 11.6%, strong enough to conclude beyond a reasonable doubt that it must be due to a relationship between drunk driving and gender in the population of drivers under 20? Or is the evidence provided by the roadside survey not strong enough to make that conclusion? And could this have happened just by chance? That is, due to sampling variability and not necessarily because a relationship exists in the population. These are the null and alternate hypotheses for chi-square test of independence. Here are other ways that the null and alternate hypothesis can be stated for a chi-square test of independence. There is no relationship between the two categorical variables. They are independent. Or, there is a relationship between the two categorical variables. They are not independent. Algebraically, independence between gender and driving drunk is equivalent to having equal proportions of who drank or did not drink for males versus females. In fact, the null and alternate hypothesis could be reformulated as the proportion of male drunk drivers is equal to the proportion of female drunk drivers, or the proportion of male drunk drivers is not equal to the proportion of female drunk drivers. The idea behind the chi-square test of independence, much like the analysis of variance, is to measure how far the data are from what is claimed in the null hypothesis. The further the data are from the null hypothesis, the more evidence the data presents against it. Here, the gender and drunk driving data are represented by the observed counts. To represent the null hypothesis, we're going to calculate another set of counts, the counts that we would expect to see instead of the observed ones if drunk driving and gender were really independent, that is, if the null hypothesis were true.
For example, we actually observed 77 males who drove drunk. If drunk driving and gender were really independent, if the null hypothesis were true, how many male drunk drivers would we expect to see instead of 77?
We'll also ask the same kind of question about the other 3 cells in our table. If the null hypothesis were true, how many female drunk drivers would we expect to see instead of 16? How many non-drunk driving males would we expect to see instead of 404? How many non-drunk driving females would we expect to see instead of 122?
In other words, we will have 2 sets of counts: the observed counts, that is the data, and the expected counts if the null hypothesis were true. We will measure how far the observed counts are from the expected ones. We will base our decision on the size of the discrepancy between what we observe and what we would expect to observe if the null hypothesis were true. How are the expected counts calculated?
If events A and B are independent, then the probability of A and B equals the probability of A times the probability of B. We use this rule for calculating expected counts 1 cell at a time. Applying the rule to the first top left cell, if driving drunk and gender were independent, then the probability of being drunk and male is equal to the probability of being drunk times the probability of being male. By dividing the counts in our table, we see that the probability of being drunk is equal to 93 divided by 619, and the probability of being male is 481 divided by 619. So, the probability of being drunk and male is 93 divided by 619 times 481 divided by 619. Therefore, since there are a total of 619 drivers, if drunk driving and gender were independent, the count of drunk male drivers that we would expect to see are the following, circled here in red. So the formula for calculating expected counts is column total times row total divided by table total. Following this formula, here are the complete tables of expected and observed counts. Importantly, the single number that summarizes the overall difference between observed and expected counts is the chi-square statistic, denoted as chi, or x squared, which tells us in a standardized way how far what we observe, that is the data, is from what we would expect to observe if the null hypothesis were true. Here's the formula. For each cell, we take the observed count, subtract the expected count, and square that value. This value is then divided by the expected count, and then this number is summed for all of the cells in the table. Once the chi-square statistic has been calculated, we can get a feel for its size. Is there a relatively large difference between what we observe and what the null hypothesis claims, or a relatively small one? It turns out that, for a 2x2 case like ours, we're inclined to call the chi-square statistic large if it's larger than 3.84. Therefore, our test statistic is not large, indicating that the data are not different enough from the null hypothesis for us to reject it. For cases other than a 2x2, there are different cutoffs for what's considered large, which are determined by the null distribution in that case. Thus, we're going to rely only on the p-value for conclusions. Even though we cannot really use the chi-square statistic, it was important to learn about it since it encompasses the idea behind the test. The p-value for the chi-squared test of independence is the probability of getting counts like those observed assuming that the two variables are not related, which is what is claimed by the null hypothesis. The smaller the p-value, the more surprising it would be to get counts like we did if the null hypothesis were true. Technically, the p-value is the probability of observing a chi-square at least as large as the one observed. Using our statistical software, we'll find that the p-value for this test is 0.201. A p-value of 0.201 is not small at all. There's no compelling statistical evidence to reject the null hypothesis, and so we'll continue to assume it may be true. Gender and drunk driving may be independent, and so the data suggests that a law that forbids sale of 3.2% beer to males and permits it to females is unwarranted. In fact, the Supreme Court, by a vote of 7-2 majority, struck down the Oklahoma law as discriminatory and unjustified.
Now we're going to use the chi-square test of independence to test the hypothesis I proposed about smoking frequency and nicotine dependence from working with NESARC data. Specifically, is how often a person smokes related to nicotine dependence among current young adult smokers? Or in hypothesis testing terms, is smoking frequency and nicotine dependence independent or dependent? That is, are the rates of nicotine dependence equal or not equal among individuals from my different smoking frequency categories? For this analysis, I'm going to use a categorical explanatory variable with 6 levels, the number of days smoked per month, which you may remember I called US Freak MO, with the following categorical values: smoking approximately 1 day per month, 2.5 days per month, 5 days per month, 14 days per month, 22 days per month, and 30 days per month. My response variable is categorical with 2 levels. That is, the presence or absence of nicotine dependence in the past 12 months, called tab 12 MDX in the NESARC dataset.
To run this in R, we use the chi-square test function, chisq.test. The chi-square test function requires 2 inputs, one for each of your variables. For easier interpretation, we'll provide the response variable first, followed by the explanatory variable. Once again, because we will need to access different attributes of the results later on, we're going to store the results of the chi-square test into a new workspace object with a descriptive name. We're going to call this workspace object nd.chisq. You can see the main test result by typing the name of this chi-square object, nd.chisq, and hitting Run. R will then return what's stored in that variable. In this case, the basic results include the chi-square statistic, the degrees of freedom to report, and the associated p-value. Our p-value is less than 0.0001, written here in scientific notation, which clearly tells us that smoking and nicotine dependence are associated. Although this tells us that there's a significant relationship between smoking and nicotine dependence, we need to look at other aspects of the results before we can figure out the direction and exact nature of this relationship. Use the code nd.chisq $observed to look at the part of the chi-square results that stores the observed counts in each cell. By now you're familiar with the $, which you've been using to select a particular column or variable from a dataset. But in R, the $sign is a general subsetting command that selects a particular attribute of a workspace object. Different workspace objects have different attributes. An object that contains the results of a chi-square test contains specific attributes called observed, expected, and residuals. So writing nd.chisq $observed is conceptually similar to selecting a particular variable from a data set, but in this case, we're selecting the attribute that stores the observed cell counts from the chi-square test function object. If you name your chi-square test something other than nd.chisq, then you'd use that name instead before the $ observed. In interpreting the results of the chi-square, the $ observed should be compared with the next step, $expected. So you'd run the code nd.chisq $expected. This table shows you the expected cell counts, that is, the counts that you'd expect by chance if the null hypothesis were true and there were no relationship between these two variables. We want more than just these numbers, though. It's most helpful to look at the data as percentages. Before we try to interpret this output, let's look at 3 tables that calculate different percentages. For our example, we're going to use percentages from a chi-square table examining the distribution of insured and uninsured individuals by geographic region. Table A shows row percentages. Each cell includes the percent of observations within each row, that is, within region Northeast, Midwest, South, and West, that are either insured or uninsured.
As you can see, adding across the rows gives us 100% of the observations within region. Table B includes the total percent of observations in each cell. Here, the percentage in each row and column add up to 100%. Finally, Table C shows column percentages. Each cell includes the percent of observations within column that is within groups, either insured or uninsured. Adding down the columns gives us 100% of observations by insurance status.
If the output is set with the explanatory variable categories across the top of the table and response variable categories down the side, it will be the column percents that we want to interpret. In other words, we're interested in whether the rate of nicotine dependence differs according to which explanatory group the observations belong to, that is, which smoking frequency group. To get these values, you use the code that you used earlier on frequency tables. The function prop.table is given a table as its first argument and then the number 2 as its second argument to indicate that you want to obtain column percentages. Prop.table parens nd.chisq $observed, 2, close parens. Now you can see the percentage of individuals with nicotine dependence, your response variable, in each smoking frequency group. Notice that we're not interested in the column percentages for those observations without nicotine dependence, indicated with the dummy code of 0. Instead, we're interested in describing the presence of nicotine dependence within the smoking frequency groups. That is, those column percentages for those observations indicated with the dummy code of 1. If we use our code
to graph the percent of young adult smokers with nicotine dependence within each smoking frequency category, I could visualize the association and see that there seems to be a positive linear relationship. That is, the more days per month a young adult smokes, the more likely they are to have nicotine dependence. I know from looking at the significant p-value of 0.0001 that I will accept the alternate hypothesis that not all nicotine dependence rates are equal across smoking frequency categories. If my explanatory variable had only 2 levels, I could interpret the 2 corresponding column percentages and be able to say which group had a significantly higher rate of nicotine dependence. But my explanatory variable has 6 categories, so I know that not all are equal, but I don't know which are different and which are not.
When the explanatory variable has more than 2 levels, the chi-square statistic and associated p-value do not provide insight into why the null hypothesis can be rejected. It does not tell us what way the rates of nicotine dependence are not equal across the frequency categories. There are, of course, many ways for the rates to be unequal. Having each of them as unequal to the other is just one of them.
Maybe there are only 2 of the population rates that are not equal to one another. To determine which groups are different from the others, we will again need to perform a post hoc test. By conducting post hoc comparisons between pairs of rates in a way that avoids excessive type 1 error, in other words, avoids rejecting the null hypothesis when the null hypothesis is true, we will be much better able to appropriately describe which population rates are different from the others. If we reject the null hypothesis, we need to perform comparisons for each pair of nicotine dependence rates across the 6 smoking frequency categories. In the case of 6 groups, we actually need to perform 15 pairwise comparisons. With these red brackets, I'm illustrating 15 paired comparisons that we'll need to conduct. As you can see, there are so many, it's actually difficult to illustrate this graphically.
If you'll recall, the family-wise error rate for 15 different comparisons is 0.54. This means that if we do not protect against type 1 error, we will be wrongly rejecting the null hypothesis and saying that there's an association over half the time. Having about a 50-50 chance of being right would obviously give us absolutely no confidence in our decisions.
So, to appropriately protect against type 1 error in the context of a chi-square test, we will use the post hoc approach known as the Bonferroni Adjustment. The goal of using the Bonferroni Adjustment is to control the family-wise error rate, also known as the maximum overall type 1 error rate, so that we can evaluate which pairs of nicotine dependence rates are different from one another.
Briefly, the process would be to conduct each of the 15 paired comparisons, but rather than evaluating significance at the p.05 level, we would adjust the p-value to make it more difficult to reject the null hypothesis. The adjusted p-value is calculated by dividing p.05 by the number of comparisons that we plan to make. So if we make 3 comparisons, we would only reject the null hypothesis if the p-value were 0.017 or less. For the 15 paired comparisons that we plan to make to better understand the association between smoking frequency and nicotine dependence, our adjusted p-value is 0.003. Adjusting the p-value is definitely the easy part of the process. Now for the more challenging piece. For the actual post hoc testing, we need to run a chi-square test for each of the 15 paired comparisons.
To do this, we can add syntax after the chi-square test in the code that outputs it. First, we need to install the package Pfeiffer. Go to Tools at the top of RStudio, click Install Packages, and type Pfeiffer in the Packages field. Then click the Install button. Then you go back to the code you've been writing and load this package by typing library parens Pfeiffer close parens. If we use the R package Pfeiffer, we can compare smoking dependence among the different groups of usual smoking frequency. We do this by using the function chisq.post.hoc and specifying the table of observed counts, nd.chisq $observed. We also tell R we want to use the Bonferroni correction to adjust the p-values to control for multiple comparisons. We use the argument pops in rows equal false to indicate that we're using column percents. And the last part of this code controls the output, so we only see those columns that are pertinent to what we're looking for within the context of this Bonferroni correction discussion. So your code reads chisq.post.hoc parens nd.chisq $observed, comma, control equal quotation mark Bonferroni in quotation, comma, pops in rows equal false, close parens, bracket, comma, 1:2, close bracket. When we look at the output of the chi-square post-hoc function, we can determine whether the column percentages from the prop.table function are significantly different from one another. To begin, we'll focus on 0.0986 smoking group 1 and 0.1846 smoking group 2.5. Are these two rates significantly different from one another? If we look down at our chi-square post-hoc test output, we can see that they aren't. So we want to accept the null hypothesis since this p-value is not less than 0.05 and is certainly not less than our adjusted or alpha level of 0.003. What about the other pairwise comparisons? Looking at groups 2.5 and 14, we can see the nicotine dependence rates are 0.1846 and 0.3516. The raw p-value associated with the chi-square statistic is 0.0299. Initially, we might want to say that this is a significant finding because it's less than a p-value of 0.05. Remember, though, that we're now comparing the p-value against the adjusted alpha level of 0.003, and therefore, the groups are not significantly different. When we examine the raw p-value for each of the paired comparisons, we use the adjusted Bonferroni alpha level at 0.003 to evaluate significance. We can see the several p-values that are less than 0.003. As we can see from further examining this chart, smoking frequency group 30, that is, those who smoke 30 days in a usual month, is significantly different than each of the other smoking frequency levels. Let's quickly summarize chi-square tests of independence. First, a chi-square test of independence is used when we have a categorical explanatory variable and a categorical response variable. The null hypothesis is that there is no real relationship between the two categorical variables. They are independent. And the alternate hypothesis is that there is a relationship between the two categorical variables, and they are not independent. The chi-square statistic is calculated considering both the observed and expected counts in each of the table cells. The Model R syntax for performing a chi-square test of independence is my chi-square test name.chisq, assignment arrow, chisq.test, parens, dataset, $, categorical response variable, comma, dataset, $, categorical explanatory variable, in parens. My chi-square test name.chisq, my chi-square test name.chisq, $ observed, my chi-square test name.chisq, $ expected, prop.table, parens, my chi-square test name.chisq, $ observed, comma, 2 in parent. If your explanatory variable has more than 2 levels or groups, you'll also need to conduct a post hoc test. We use the Bonferroni Adjustment to protect against type 1 error, and then run the chi-square tests of independence for each paired comparison. Now you're ready to test a categorical by categorical relationship. Also, if your own research question is a quantitative to categorical relationship, it's a good idea for you to categorize the quantitative explanatory variable and test the association with the chi-square test of independence.